All right, acids, bases, and pH. The dissociation of water means that you have a reversible reaction of water changing from water to hydrogen ions and hydroxide ions. And this is reversible. It's going to happen both ways, right? So when we talk about acids and bases, I'm going to skip the pH scale. Well, the pH scale is used to measure the degree of acidity. It's a range from 0 to 14. And we're going to talk about how those numbers mathematically come to be once we define acids, bases, and pH. If something is acidic, it's going to, or let's say an acid. An acid is a substance that has a relatively high concentration, this is a symbol for concentration, of hydrogen ions. It removes hydroxide ions because it tends to combine with hydrogen and form water. And in our example, we're going to use hydrochloric acid. A base, let's undo that. A base, I'm just going to add it in here, is going to be a substrate that has a low concentration of hydrogen ions. It may have a high, let me undo that, sorry, a high concentration of hydroxide ions. This is going to be something like NaOH, sodium hydroxide. Now, if something is acidic, like what I changed up here, switch colors, it means it has a pH between 0 and we'll say 6. And basic has a pH of, let's do 8 to 14, with neutral being 7. And these are in aqueous solutions. Strong acids and bases dissociate completely in water, like HCl and NaOH, and weak acids and bases dissociate only partially and reversibly. So the pH scale is the negative log of your hydrogen ion concentration. I changed colors there, and this is going to be in moles per liter. Now, what that means, we're going to do some math with this tomorrow. But you need to be able to move up here to this corner and say, if you look at pH, the pH scale is the hydrogen ion concentration, hydroxide, OH, negative. And that should, those together equal 1.0 times 10 to the negative 14 in aqueous solution. Neutral, if you have a neutral solution, we've said neutral is 7 hang on. Neutral, since it has a pH of 7, its hydrogen ion concentration is going to be 10 to the negative 7 molar. But if it asked you what the hydroxide concentration is, you have to look at the exponents. We want it to equal 14. So we need another negative 14, negative 7. I'm going to do one more, and then we'll do a lot of these tomorrow. Let's say your hydrogen ion concentration for a substance is 10 to the negative 5 molar. That means your pH is 5, and it means your hydroxide ion concentration is 10 to the negative 9. Because again, this and this need to equal 14. All right. What else is on this page? Buffers. Buffers are substances that prevent large, sudden changes in pH. These are important because they control chemical reactions and help to maintain homeostasis. Almost done, baby. And then acid precipitation. Hang on. Sorry about that. Acid precipitation can be rain, snow, or fog. And it's going to have a pH of less than 5.6. It can be as low as 1.5. There's a example in your book in West Virginia there. This occurs when sulfur oxidizes and nitrogen oxides in the atmosphere react with water in the air and form acids which fall to earth. A major oxide source, is combustion of fossil fuels. The effects is it lowers the pH of soil, which affects mineral solubility, and so it can leach out mineral nutrients.
They had the iPad?
Not yet, baby. Hang on. Hang on. Sorry. Minerals can leach, or you can leach out mineral nutrients, and it may increase the concentration of minerals that are potentially toxic to vegetation in high concentration. It also lowers the pH of lakes and ponds, and the runoff carries leached out soil minerals into aquatic ecosystems, which is not good. In the western Adirondack Mountains, there are lakes with a pH of less than 5 that have no fish. So you need to, what could be done about this? You could add industrial pollution controls, develop the use of anti-pollution devices, or increase the involvement of voters, consumers, politicians, and business leaders.